Oof, that's not right. Oh, what fresh hell is this? Hello Internet, my name is Quinn, this is Blondihacks. I'm back on the Pennsylvania A3 switcher project this week, and we finished the rolling chassis for the tender. Now it's time to go upstairs and do some body work. I'm going to get started on the water tank for the tender. It's a big, cool structure that I think you're going to like, so let's go. They say you should start every YouTube video with a big dramatic moment. And well, nothing says drama quite like a spreadsheet, so let's start there. Now, if you don't think spreadsheets are big and dramatic, wait till you find out the number at the bottom right is what you're going to have to pay for all of the materials for the next section of your model locomotive. This being a new milestone, if you will, for the project, I'm going to start the same way I have with all the other milestones, which is to go through every single drawing of every single part in the section of the book and figure out all the materials I'm going to need to make all those parts. Then I add all of that up, I go check what I have in the shop already, subtract all of that, and then make a giant shopping list, usually at McMaster, for all of the exotic materials that I will inevitably need. This process is a little tedious, but it really speeds up work in the shop because you don't have to ever stop and wait for materials to be shipped, and you can just keep making chips until all the parts are done. The star of the show for this next section is this giant piece of copper. This was not inexpensive, however it is very thin, so that helped quite a bit. This is half the thickness of all the stock that was used on the boiler, but it is very large, and you'll see why here shortly. There's some other also large brass parts on this section. We're making all of the big body panels on this part of the build, so there's a lot of really big sections of material that are needed. And these sections are not cheap, but luckily there's not many more of these that we need. The rest of the locomotive is pretty much all bar stock, which is much cheaper. Speaking of bar stock, we need quite a bit of that as well, in various shapes and sizes for the ribs and other things that hold all the body parts together on the tender water tank. As with other sections, I went down to the local library and they very kindly made copies of all the pages of the book so that I can put them in a binder, use them out in the shop, scribble notes on them and so on, and not get the really beautiful and not inexpensive Kozo book dirty. Okay, let's make some chips. First up is the tender floor. This forms the bottom of the tank and the floor of the tender. And this is a very big piece of brass plate. It's 24 bananas by 12 bananas and a whopping 94 thousandths thick. This is definitely a plate and not sheet metal. This is quite a heavy piece and probably the largest single piece actually on the entire locomotive. So working with this had a few challenges. I had to start by rough cutting it to size, as with most of these parts. However, the size of this piece meant it was quite a bit too large for either my portaband that you see here or even for my larger bandsaw. Both of those saws have about the same throat depth, and neither of them had enough throat depth to do all of these cuts in one go. I was able to work around it by making a few offcuts into the scrap material, but I was trying to strike a balance between mangling up my offcuts, because larger offcuts are more useful later, and still being able to make the cuts with the bandsaw. So I did a compromise. I cut up some of the scrap material, but also ended up finishing this one last cut by scoring with the Dremel and snapping it on the edge of the bench. That allowed me to save at least this one last big piece without having to chop it up to get access for the bandsaw blade. To square up all of those edges, my first thought was to go straight to the fixture plate and my sheet metal bar clamping system that I developed exactly for pieces like this. I used it a lot on the boiler. However, I immediately realized that my sheet metal clamping bars are comically undersized for this piece. As I said, this piece is quite a bit larger than anything else I've done yet on this project. So this is not going to work. I switched gears then, and I'm going to do this right on the table. The edge of my table is proud of where the cover for the DRO scale is, so I can cut off the edge of the table. And I found this long piece of flat bar in the scrap bin, and I've got it set up on edge where it'll be stiffer, and I can use this to clamp down the sheet of the material against the edge of the table. So I'm lining up the bar right on the edge of the table so that it's kind of like an opposite clamping jaw from the edge of the table. I want to make sure the material is supported orthogonally across the cut line. Then I spaced it just a little bit off the table, as little stick out as I can get away with and still make my cut, and make sure it's relatively straight. This edge that I'm using first is a factory cut edge, so it's nice and straight. It's a good starting point. However, it is a shear cut, and shears cut with a pinching action that distorts the material. So I want to cut deep enough to eliminate all of the artifacts of the pinch cut. I want to end up with square virgin material on all sides of this piece. Pinch cuts ended up looking weird if you can see them in the final parts. Then some very careful cutter setup so as not to hit my table or my DRO scale, and away we go. I can clean up this edge, get it nice and straight, and get rid of the pinch cut artifacts. I did find in the middle the piece was vibrating a little bit. The clamping bar is of course not clamped as well in the middle. I didn't have any strap clamps that could reach into the piece that far. So I added one more piece to my setup, which is a Precision Starrett Toolmaker's brick. This is a special order item. It's not in their catalog, but I happen to have one, and this took care of the vibration when the cutter was in the middle of the part. As is always the case in a setup like this, that spindle is going to get close to your clamps. Luckily, my many years of playing video games have trained me for this moment. I'm watching that, make sure that spindle's not going to touch that clamp. I'm ready to stop the power feed if it's getting too close, and boy, it was close. But clearance is clearance, Clarence. With one side cleaned up and straight, I can now flip it over and make the other side straight, parallel, and bring the piece down to dimension. I have to indicate in this side to make sure that the far side that we cut will be parallel. I can do that with a dial indicator and a little judicious tappy tap tapping. That's running nice and parallel now. Beautiful. And away we go down the other side. You can see I've added some Mitutoyo painter's tape to the setup to keep vibration from causing the Starrett Toolmaker's brick from moving around on the piece. That's a pro tip I got from a tool and die maker. Once that's down to dimension, then I turn the piece 90 degrees and I indicate in one of the long machined sides that we just did so that the ends will be cut square to these long sides. Once again, I clean up one end, making sure to remove the factory pinch cut, and then flip it end for end, dial it in again, and machine it down to dimension. Now getting the dimension on the long side was a little tricky. I don't have a caliper big enough for this measurement, so I did have to use a scale and some magnification. But if you have a good quality scale with good markings on it and lots of magnification, you can get within 5/1000ths doing that, which is well within the tolerance for a piece like this. For the next step, I'm going to use a different type of material. You don't see me use a lot. This is an expanded carbohydrate product. This particular alloy is called OAK, specifically red OAK. It comes in red, green, and blue like Loctite. It's easy to cut, it's pretty lightweight, and it's very sturdy. It makes great hammer forms. Something you might not know is that you can use these new high-tech alloys for hammer forms. Really good stuff. This first piece that I cut off is going to act as a waste board for a whole bunch of drilling that we need to do on the tender floor. There's a ton of pieces that attach to the floor of the tender, so we have to drill a huge web of holes all over this thing. And putting a nice parallel planed board underneath is just going to make this so much easier. So I centered it up on the long axis with the edge finder, and then I found one end because all of the holes on the drawing are dimensioned from one end and from a center line, which makes it super convenient for the DRO. If I center up my origin on that same point, then I can just run through the diagram, moving to each position, drilling the holes in turn. There are a lot of these holes, different sizes. Some are threaded, some aren't, some are countersunk, some aren't. It'd be really easy to screw this up, so I'm taking my time, double checking everything, and crossing off holes on the drawing as I do them. The trickiest part is that a whole bunch of these holes get countersunk, but they all get countersunk from the other side. Now it would be very tempting to do this piece upside down so that you can do all the countersinking in this same setup. However, that would mean you're reading the drawing upside down, and that is really asking for trouble in my experience. I have learned the hard way. Don't try to flip a drawing in your head. You will screw it up. It's better to do two setups than to try and be clever and save yourself some time. There were some interesting sub-clusters of holes like this one. This is a 3-hole bolt circle that goes around a larger hole. I believe this is the mount for the water fitting from the water pump that lives inside the water tank. The 2 large holes there, I believe, are the mounting points for the water pump. So there were some neat DRO side quests like that. Another gotcha moment, 2 of these holes are countersunk from the top, and the rest of them are countersunk from the bottom. Luckily I caught that, but it would be very easy to screw that up and countersink something from the wrong side. That's definitely the kind of mistake I usually make reading these drawings. With all the holes drilled, I'm now going to flip it over to do all of the countersinks, which are, as I said, mostly done from the other side. I did not bother, however, to re-indicate this in and redo all the edge finding and so on in order to use the DRO to position all the countersinks, because countersinks don't have to be that accurate. Within a few thousandths is plenty for a countersink. So I just lined up each hole one by one using the back end of the drill that was used to drill that hole. And then once I'm lined up on it, I swap out for the countersink, I countersink that hole, and then I move on to the next one. And that way, no alignment is required on the plate. I can just go hole by hole, line up the countersink on each one, and do it. It might sound tedious, but I think it's actually a lot quicker than re-indicating in the plate and redoing all the edge finding, which is quite a bit of work. Well, with 30-something holes, all in very specific places, did I get them all right? Well, some of them we won't know for quite a while, but I definitely got at least one of them wrong, as I found out when I did a test fit on the chassis. That's the drawbar pin at the front, which goes through the tender floor and acts as kind of a nice alignment for everything else. All of the mounting holes to the chassis look correct, except these two at the back do not line up with the rear chassis crossmember. That's a little strange. I wondered how that happened. Either the crossmember is wrong or the holes in the floor are wrong. So I checked the drawing for the frame, and I got the measurement for where the crossmember is supposed to be, and that is right on the money, so that's in the right place. Then the measurement for the holes in the floor, 12 and 5/16, that's right where I put them, except, yeah, that dimension was a chain dimension off of this little 5/16 up by the origin. I thought it was an absolute dimension from the origin. Yeah, chain dimensions are trouble. They will get you. You really got to watch those. Luckily, the error was large enough that I could then drill the holes again in the correct place, and they weren't too close to the old holes. So I have a couple of speed holes in the floor that actually might need to be plugged because they're going to be speedy water leaks, but at least it was an easily fixed minor error. One other little error I noticed at this point, turns out the rear bolster was supposed to be 1/8 of an inch wider than the frame. I didn't catch that in the drawings. I thought it was supposed to be the same width as the frame, which made sense to me. So the corner of the tender floor looks a little odd because it sticks out wider than the frame at the back. So I think what I'm going to do is just knock those corners off, put a little chamfer on that, and make that transition look intentional rather than have that awkward corner sticking out. But we'll deal with that later. Back to that waste board now. It's going to be resurrected as the hammer form for the tender tank. I need a former and a backer. If you watched the boiler making series, then you know all about what's about to happen here. Very much the same process. The corners all need to be rounded with quite a large radius on this former. One of my viewers took pity on my not owning a proper set of drafting tools and sent me this really beautiful compass set. You can see what a beautiful, beautiful curve it's making for that form. It would be even more beautiful if it was in the right place, which it is not, so I moved it inboard as you see. Fun fact, that's still in the wrong place and I had to move it in again. Now, in my defense, the drawing for this former is, I will say, not great. Most of Kozo's drawings are beautiful and extremely accurate, everything you need. For some reason, however, the drawing for this former is only shown in one isometric view, and several of the key dimensions are obscured by decorative lines that don't show you what they're referencing, and let's just say it was difficult to interpret that drawing, and it took me a few tries to get this right. Luckily, all the errors were in my favor. I just had to keep making it smaller as I realized what the drawing was trying to say. So I rough cut this out on the bandsaw, and then to finish this down to the lines, I went ahead and used my belt sander. If you watch the boiler series, you know that we used a lot of elaborate rotary table setups and complicated fixtures to make every radius and every line perfect on the wooden formers. That really isn't necessary here because the tender tank parts are much lower precision, and unlike the boiler, these parts don't have to fit perfectly within 1,000th to 28 other hammer-formed parts, so the formers can be much lower accuracy, and belt sanding down to the layout lines is plenty good enough for this, which is great because this is a whole lot easier than a very complicated milling setup. The top edge of this former needs to have a radius on it to form the curved corners of the tender tank. Now I decided to do this with a router and a 1/4 inch roundover bit. However, in the drawing, for some reason, this radius is actually specified as 0.270. And I have no idea how you would create a 270 radius on a piece of wood like this. There's no roundover bit that you can buy for a router or a milling machine that's that radius. I guess you would have to hand sand it very meticulously. Maybe there's a metric one that would be close. I don't know, but I decided 250 was close enough. Again, these details are all aesthetic, and I don't think it's going to matter if my radius is a little bit smaller than the one that Kozo specified in the drawing. So a hand router done outside because of the mess made quick work of that. Sidebar, if you are a woodworker just getting into machining, routers are your single best learning tool for learning the difference between climb milling and conventional milling. If you've used a hand router, then you know if you try to mill clockwise around the outside of a part, the router bit will grab and pull the router out of your hand and make a mess. That's climb milling. The same thing happens on a microscopic scale to the milling machine, and that's why you always want a conventional mill or mill in a counterclockwise direction. The tender tank backer then was made the same way. It doesn't need the corner radius, and it's the same shape, just smaller. The backer, of course, is needed to keep the piece overall flat while we hammer the edges of the flange around those sharp bends. All right, we're ready for copper now. I have to cut out a very similar shaped piece from the copper sheet. Luckily, again, the dimensions for all this are in the book, because figuring out the exact dimensions for a former to create the final part dimensions that you want, and then figuring out what dimensions should be on the sheet metal to bend around all the corners and land in the right places, that's all some pretty tricky math, but Kozo has done it all for you. So you just have to lay out all the pieces to his spec and you will be fine. Or mostly fine, as you'll see. Now I double and triple checked all of these dimensions before I cut anything, but I did have a little bit of trouble towards the end, as you'll see. Now I was hoping this material was thin enough to use my shear. I did a test cut on one corner and it did it, but just barely. There was no way I was going to be able to cut that sheet full width, so even though it's copper, it's still 40 thou, which is a little too much for my little baby shear. So I had to do it on the bandsaw again. And then once again, I cleaned up the edges on the belt sander, just sanding down to the layout lines. Again, not a lot of precision needed here because these edges will just be the outside edges of the flanges, which will be entirely inside the tender when we're done. All these are surfaces for which we can solder the adjoining pieces to, so they don't have to be very accurate at all. One last double check on the former before I proceed, and it looks pretty good. I was starting to notice that it looked a little short on the ends, but it was close, so I thought, well, it's probably okay, and I decided to go ahead, take it over to the hearth and anneal it so that we can hammer form. And annealing, of course, if you watch the boiler series, you saw me do lots of this. Take a torch, in this case a very big one because it's a big piece of copper. It's going to take a lot of heat to get it all up to temperature. You heat it until every area of it has been a glowing reddish orange for at least a few seconds to get a really thorough, deep anneal. The better your anneal, the easier the hammer forming goes. If you find yourself having to re-anneal a lot during this process, it probably means you aren't annealing enough. This whole hammer forming that you're about to see can probably be done in 1 or 2 anneals. I ended up doing 2.5, as you'll see. And let that cool naturally. Resist the urge to quench it, because a piece this thin and large, you will definitely warp it if you quench it. You won't harden it. Copper alloys don't harden when quenched, but you will warp it. So let it cool in the air naturally, and now I can clamp it back to the former and the backer. The important point here is to get it properly centered on the former all the way around. So I took my time here, taking lots of measurements and tapping that piece of copper into position. I want to make nice and sure this is centered. We only get one shot at this. And now comes the fun part, the hammer forming. If you watch the boiler series, then you've seen lots and lots of this. This, I will say, was a whole lot easier. This material is half the thickness of the copper used in the boiler, and this hammer forms really, really easily. But that said, I'm still following the #1 rule of hammer forming, which is don't get greedy. You tip the edge a little bit at a time, going all the way around. Don't try to tip one section of the edge all the way over. You just want to work your way around, doing a little bit at a time. And you might feel it getting harder and harder to bend, and if so, it might need annealing again, but I got basically 99% of the way on a single anneal. This material is so thin that it really had no trouble forming itself over this former. You'll notice I didn't do any kind of alignment pins through the piece. Honestly, my experience is with copper, that just isn't necessary. After the first round of hammering, the piece is already so close to the form that it goes right back where it was anyway, and any kind of pins just aren't needed. So I annealed it one more time to get all of the remaining flanges nice and tight. The second annealing was needed mainly for these corners, as you might guess. Around these corners with the radius and everything, we're really asking this material to shrink a lot. There's a lot of material that we need to squish into itself into a much smaller space. So it doesn't like to do that. So you're going to have to do a lot of tapping. As you can see, it's fighting. It's going to try to spread the material out around the sides. You're going to have to re-straighten the flanges around the corner and keep hammering that corner, and just don't let it go anywhere except where you need it to. And eventually you will get it. That little peak that's left there got very hard at the end. It was not happy about what I'm making it do, so I have to do one more annealing just for that little peak on each of these 2 corners. That's why I say I had 2.5 annealings. So here's the final heating, And let's see if we can get that done. In fact, on this last annealing, I just annealed the corners. I didn't bother doing the entire piece. As you can see, that was enough to get it to pile up on itself and close up that corner nice and tight. It really is beautiful watching how annealed metal will shrink around a corner and basically pile up the material inside itself to fit into a smaller space than it used to. It was a little tricky to remove. It's a big piece and it's such a close fit on the former when you're done that it can be quite stuck on there. But that is looking pretty good, I think. I ran it through the pickle bath to clean it up for the next few operations that we need to do. It looks really good. My only concern is that the flange depth looks a little short on the ends. That was the concern I mentioned earlier. See, the sides here look good, but the ends, that flange is a little short. I think it'll be okay. The pieces that attach to this attach right at the corner radius, so I think it'll be okay. If it's not, it won't be a huge deal to graft in some pieces to fill any gaps that we have. This is just a water tank, not a pressure vessel, so we can get away with a lot more. The center line that I scribed when I laid out this copper is still there, and I want to double check now that it's still valid, that it survived hammer forming. It looks like it did, so I can use that as my reference for splitting the tank sides apart now. After doing some measurements, I noticed that the extra material between the two halves is exactly 70 thou. Now the Kozo's intention is that you would use that 70 thou to split the pieces with a fret saw or a bandsaw and then file the pieces flat. Now that's not a lot of wiggle room, 70 thou, to do all of that, so I thought I might have better luck splitting the pieces with a 1/16 end mill. That will split the pieces with a very small amount of kerf and leave perfectly machined sides and leave me within a couple of thousandths of dimension, well within tolerance. I've got the piece set up on the mill table and I've got the pointy end of my edge finder in the spindle. I'm going to use that to align the center line with the spindle and of course also with the T-slot in the middle of the table so I can cut through without hitting the table. Lots and lots of light, lots and lots of magnification gets me aligned with one end. Then I run down to the other end and I tap the other end in to get that end aligned with the table. And then I run it all the way down and make sure that both ends are still on my scribe line. Again, lots of light, lots of magnification for accuracy. And I'm dead nuts on the line at both ends, so I am aligned. And in goes the tiny, tiny 1/16 end mill and a lot of lubricant and more than a few prayers to Metallicor, the god of machining. I am very likely to break this end mill, but let's see what happens. Your best tools for avoiding snapping tiny end mills are lots and lots of RPM and very slow feed. You need a ton of RPM to get the correct surface speed on an end mill this small, so you got to make sure it's cutting properly. And you want to feed very slowly because these tiny end mills can't handle any kind of lateral cutting loads or you will snap them, so feed them very slowly. You can see I'm also nursing this cutter like a baby bird, making sure that the chips stay clear of it, and then it's got lots and lots of cutting lubricant on it. I'm using WD-40 and basically flooding it. Flood coolant would be a good idea for a cut like this, but I do a cut like this once every 2 years where flood coolant is really necessary, and it's just not worth setting up all of the mess and hassle of a flood coolant system for the occasional use that I would have for it. Once in a blue moon like this, just lots and lots of spray bottle action, and my blowy air thing works just fine. That blowy air thing, by the way, is a rocket air puffer for cleaning camera lenses. That was sent to me by a patron. It's incredibly useful for clearing chips. This was going incredibly well, as you can see. I had to stop here and move a clamp, and I decided to crank it back by hand to get a run up at the cut again, and tink, yeah. That was me breaking the end mill, all because I moved the table backwards in the cut with the cutter not spinning, and so it snagged, and that was all it took to break it. If I had done that with the cutter running, it would have been just fine. So aside from that one brief moment of user stupidity, everything went great on this cut. This was a double-ended end mill, so I flipped it around, used the other end, and finished the cut, no problem. There's not enough flute length on this to cut the flanges, so I had to stop short of those and finish those by hand. But you can see what a beautiful job that did. Those are perfectly machined edges in between. I won't have to do any finishing work on that at all, and I'm going to end up right on dimension. So I cut through the flanges down to my slot with a fret saw, and the fret saw kerf was thinner than that 1/16 end mill, so I just had to finish those cuts up with a little bit of filing to bring them down to the machined edges. And I gotta say, that was definitely a great way to do that. That worked out super well. It wouldn't even have cost me an end mill if I'd been paying a little better attention. Honestly though, I consider those 1/16 end mills consumable. They're so tiny. My record on breaking them is about 50%. Every time I need them for an operation, I pretty much break them about half the time. It's very difficult not to. Or maybe if you're a better machinist it isn't, but I have trouble not breaking them. Next up are some brass structural ribs that go along the bottoms of these sides. So I'll rough cut these to length, one for each side. These are simple parts. The only trick is that they need to sit inside the sheet metal. So the ends need to be filed to fit these little curves that are at each end of the copper. So I traced the shape on there. That'll give me a rough guideline to file down to on the die filer, but I'm going to be doing lots and lots of test fitting as I go. I'm not going to trust that line too much. The die filer was the perfect tool for this. It really made this go quickly. I was able to do a little bit of filing at a time, test fit, file a little more, test fit, and so on. At the small end, I also needed a little bit of a compound curve because the top corner radius impedes on the end corner radius a little bit right where the brass bar is. So that was a tricky fit, but I'm pretty pleased with that. This doesn't have to be, again, as perfect as the boiler because these parts are going to be soft soldered together, and soft solder is much better at gap filling than silver solder is. Now I'm able to mock it up on the tender floor. The trick is I got to make sure that wherever the bolt holes land in these ribs, that the back of the sheet metal on the tender ends up in the correct place on the tender floor. So a little bit of mock-up ensured that. I was able to scribe a line for where the frontmost hole should go. Then I lined that up on the mill spindle with the pointer once again, and then the rest of the holes on this rib were all done with the DRO because I know the spacing of them just has to match what's on the tender floor. Those all get tapped for the mounting bolts that hold this to the tender floor, and now we're ready for soldering. Well, almost. I clamped the rib in place where its final position will be, and then I drilled and tapped for some tiny fixturing screws that are going to hold everything together during soldering. And now we can flux up the bar, put the screws back in, and do the soldering. Once again, this is plumbing solder that I'm using, soft solder, not silver solder. This is just a water vessel. It doesn't have to hold any pressure and it doesn't take any heat, so it doesn't need to be silver solder, which is great because soft soldering is a whole lot easier than silver soldering. It's almost comical how little heat is required. I'm using my smallest torch and this is almost too much, frankly, for this little job. These are big pieces too, but soft solder just needs so little heat that it just, you look at it funny and it flows. Ugh. It's kind of a joy after all that silver soldering. A bit of cleanup and inspection. Looks like that will be a watertight joint, so I think we're going to be okay. If it isn't, soft solder joints are super easy to repair after the fact, again, unlike silver solder. And then finally the fixturing screws get their heads filed off, and it'll be like they were never there. These tank sides will be powder coated, but in fact there's also going to be brass decorative cover plates that go over top of them, so you're not really going to see any of this in the end. All right, final test fit on the tank floor now. Can get the screws in there, feed them in from below. You can see now why the countersinks for the tender floor on the bottom are so important, because all of these screw heads need to be sitting flush or below flush so that the assembled tank will sit flat on the frame of the tender. With both sides in place, I'm able to do some checking of final dimensions on everything, check that the sides of the tank are the same height and that they're parallel and everything's the correct height from the drawings and so on, and everything looks pretty good. The angle on the back of my tender is a little bit different than Kozo's, so I did make some kind of small error there, I think, in my sheet metal cutting or my hammer form or something, but I think it's close enough. Once again, I'll mock it up on the chassis and put a few screws in partially to kind of pin it in place, and we can get a look at the final result. I'm really excited by this. It's kind of shocking what a difference this makes as far as making it look like a tender. I mean, we're still in the very early stages of this water tank, but you can really now get a feel for what this tender is going to look like, the size of it, the proportions of it. I think it's going to be beautiful. I'm really excited to get to this point. I hope you are too. We have lots more exciting operations to do to make this into a water tank, and we haven't even started on the coal bunker yet, so stay tuned for all of that. Thank you very much to all of my patrons for making all of this possible, and thanks to you for watching, and I will see you next time.